Now for an example, I mentioned that you'll generally be asked to create the equation of the path if you're going to have to use it. But in this question, we're given the equation of the path here in blue, and we're asked to do some things with it because it would be silly for me now to show an example where I have to create the equation of the path when I've just shown you a video that does that. And you will sometimes get questions where they're giving you the equation and just seeing if you can rearrange it and use it somehow. So we've got the equation of the path here. Part A says we need to show that the horizontal range on level ground is this, and then find the maximum range. Now here's something confusing. When we looked at functions in year 11, we learnt that domain was what x could be and that the range was what y could be. And yet when we're talking about firing projectiles, people talk about the range of a certain weapon as being how far it can go. So in that way, we're actually looking at what x can be and how big it can get. So the maximum range is going to be the biggest extent of x. So we have our formula here, we just need to rearrange it. We need to find the horizontal range. Now think what happens if we've got a projectile doing this on horizontal ground. It's being fired from here and it's landing out here somewhere. It's basically an upside down parabola. So if the formula, it's starting at the origin and this is y and this is x and our formula is y and it's in terms of x, then clearly we need to let y equal 0 to find the intercepts of this thing. So start by stating what you're going to do, let y equal 0, and then go ahead and do it. Now there's various ways you could tackle this. You could just rewrite this with a 0 and then factorize, or you could say if this is equal to 0, then something minus something else, these two things must equal each other, and you could try and equate them. Take your pick. Some people will prefer it one way and some will prefer the other way. I think your textbook example equates the two, but I think that for me factorizing makes a little bit more sense. Okay, so I'll start by just writing it out, but given that I want to factorize it, it makes a bit of sense to look ahead and think about what you'll be able to factorize. I can see that I can bring an x out of both terms, but it'd be nice to be able to change these into some sort of form that I can factorize. Now tan of theta is sine theta over cos theta, and sec squared theta is 1 over cos squared theta. So I think I'll rearrange them like that so that I can bring 1 over cos theta out the front of my brackets. So I'll write it that way. I've got multiplied by 1 over cos squared theta plus alpha, not theta, over cos alpha. Then on the next line, I can clearly bring an x over cos alpha out the front, and that leaves me with here minus g x squared on 2v squared cos alpha, which is a bit of a mouthful. Sorry, not x squared, just an x. And then over here I've brought those two terms out, so all I'm left with is this one. So now I can see that if something multiplied by something else is 0, one of the parts must have been 0. So therefore x over cos alpha is equal to 0, in which case x would be 0. Or I've got minus g 2v squared cos alpha plus this is equal to 0. Now if these two things are equaling 0 and one's positive and one is negative, I could just say that this is equal to that. That's going to save me a line. Now I'm trying to get it in terms of x equals something, so let's multiply both sides by the denominator here and divide by g. So I'll have 2v squared cos alpha multiplied by what was already there, the sine alpha, over g. Now looking at my question, show that the horizontal range on level ground is this. V squared on g, well that's looking good, but then I've got 2 cos alpha sine alpha, and they've got, actually this is a mistake in the question, it's meant to be sine 2 alpha. That'll help. Now keeping an eye on your finish line helps you to see whether you're getting there or not. The only thing I need to change is the 2 cos alpha to sine alpha into the sine of 2 alpha, and they do equal each other, so I can go ahead and say that that is v squared over g sine of 2 alpha, and I'm there. So x equals 0 or x equals this. So I've shown that the horizontal range is that because it goes from, as it goes along the ground here, from where it's shot out to where it lands, it goes this far. Now, how do I maximize this? Find the maximum range. We've done a lot of maximizing of things by differentiating and letting the derivative equal 0, but I can also see that as a function of alpha here, when sine 2 alpha is as big as it can get, then my range is going to be as big as it can get. So a quick sketch of y equals sine 2 alpha, what does that look like? Well, it goes along like a normal sine curve, and its period is 2 pi over 2, which is just pi, which means that this is pi over 2, and this is pi over 4, or you could be working in degrees here and saying this is 180, this is 90, this is 45 degrees. We can see that we get the highest value for sine 2 alpha when x equals 45 degrees. Or sorry, when alpha equals 45 degrees. So we can just write that down. When alpha equals 45 degrees, the sine of 2 alpha equals 1 and is at a maximum. So when it is equal to 1, our range, when alpha equals 45, range is going to be equal to v squared on g, because this whole section here will just be 1. Does that make sense? All right, the second part of our question now, arrange the equation as a quadratic in tan alpha and show that a projectile can be fired through a point xy if and only if this inequation is satisfied. Okay, so to make our equation of the path into a quadratic in tan alpha, we need to get it in terms of tan squared alpha, tan alpha, and some numbers, and get it all equaling 0. Then we can look at what tan alpha could possibly be, and hopefully we can come up with something like this. This is our finish line, so we keep an eye on that as we go. So in my first line, I'm just going to rearrange the parts that need to be made into tan squared alpha, which is this part, which is tan squared alpha plus 1. So we've got minus gx squared over 2v squared bracket tan squared alpha plus 1 plus x tan alpha. Okay, let's expand our brackets out now. So y equals minus gx squared over 2v squared tan squared alpha minus gx squared over 2v squared, because we've multiplied that by 1, plus x tan alpha. Okay, next let's get rid of fractions. So we'll multiply all of the terms by 2v squared. And we want to get everything onto the same side, I suppose, as well. So let's just do one thing at a time. We've got 2v squared y is equal to minus gx squared tan squared alpha minus gx squared plus 2v squared x tan alpha. Bit of a mouthful, but we're getting there. Now let's get everything onto the same side, and let's have a positive number of tan squared alphas. So we'll bring everything over here. So we've got gx squared tan squared alpha. That will be our first term with the tan squared alphas in it. And now we want to put the term that's got tan alpha in it. So if we subtract that from both sides, we've got minus 2v squared x tan alpha. So there are our tan squared alphas, our tan alphas, and now we need the other terms and then equal 0. So if we add this term to both sides, then we'll have plus 2v squared y plus gx squared, and all of that will equal 0. So when we're working with solving quadratics, we know that we can use the quadratic formula when we can't factorize, and this is a situation like that. So if you want to note down your ingredients here, if you like, the number of tan squared alphas we have is a, and that's gx squared. B is the number of tan alphas that we have, and that's negative 2v squared x. And C is all of this, 2v squared y plus gx squared. Now, let's read the question again. Show that a projectile can be fired through this point xy if and only if all of this happens. Now, have a look at what's in there. There's no alphas in there. So clearly we're solving it. We're getting it in the form of a quadratic in tan alpha, and then we're solving that to some extent, or we're thinking about when there is a solution. Now, if we want our projectile to actually go through the point xy, then there have to be values of x and y that make this true. And that means if we just let the discriminant be greater than or equal to 0, then we'll have some solutions for x and y. So remember the discriminant, if you're a bit rusty on this, is just b squared minus 4ac. And so we need to take that and we need to make it greater than or equal to 0. So our next line of working would be to say, all right, it's quite handy having written out what b is. If we square that, -2 squared will be 4. The v squared will be v to the 4. That's looking good because that's in our formula. And then we'll need to square the x as well. So that's our b squared minus 4 times a. Let's just chuck it in brackets. So we remember, it's not so much that we need the brackets, it's so we can remember what we've done and we don't get confused. We've got 4 times a times c, where this is c here, 2v squared y plus g x squared. So all of that has to be greater than or equal to 0. And including that sign is handy because I can see my finish line and it's got that sign in it. So keep looking at that for clues. All right, I need some terms on each side, and clearly my finish line doesn't have brackets. My line does have brackets, so the obvious next step is to tidy up and expand brackets and then just move things around a little bit. So it'd probably be easier in here if I actually just take the brackets off that part because I need to expand both terms. I've got 4v to the 4x squared minus 8. What do I have here? V squared g x squared y. V squared g x squared and y in whatever order. And then I've got minus 4 g squared x to the 4. And all of that is greater than or equal to 0. Okay, so we've got 4, 8 and 4, and up here we've got 2, 1 and 1 as our coefficients. So just keep looking at that as a clue to what to do next. Let's divide everything by 4. So we've got v to the 4 x squared minus 2. And let's start getting things in the same sort of order. Let's put v squared first here because this looks like this term. And then we've got g, and then we've got y, and then we'll put our x squareds. And then we'll put 4g squared x to the 4 is greater than or equal to 0. Now, can you see a really strong difference between this line and our finish line that we're going for? Seems like the x's are not quite right. We've got x squared here, and x to the power of 4 there. Whereas here, there's no x's, and there's only x squared. So if I divide everything, sorry, I needed to have just a 1 there, don't I? Divide by 4, divide by 4, divide by 4. Sorry, I lost the plot, made a mistake. I think I fixed it now. Okay, so we need to basically divide all terms by x squared. Now, normally dividing by your pronumeral is kind of a no-no, but the reason for that is it stops it from being allowed to be 0. But could x be 0? Not really. It's a point somewhere in the air that we're trying to fire our projectile through. So x is not equal to 0, and I can just jot that down that we know that to be the case. Therefore, it should be okay to divide by it. So now we've got v4 minus 2v to the power of 4, I should say. gy minus g squared x squared is greater than or equal to 0. And now we just need to rearrange it. We'll put this part on the little side, and these guys can stay on the big side, which is how they are. And so we're pretty much there. Therefore, 2v squared gy is less than or equal to v to the 4 minus g squared x squared as required. And the last bit now, rearrange what we were just given there in blue to make y the subject. What does this mean geometrically about this point xy that our projectile is going to go through? All right, making y the subject, at the moment the y is all caught up with this, so we really just need to divide both sides by 2v squared g. So we'll get this. Now, we could leave it like that, or we could rearrange it so that we're dividing the fraction up. Now, v to the power of 4 over all of this, the v squareds will cancel, so we will get v squared over 2g minus, and this term here, we'll end up with one of the g's cancelling, so we'll just have gx x over 2v squared. Oh, yep, that's right. Hold on, no, I'm missing something. Here, that's a squared. So is that, and so is that. All right, so we've rearranged it. I think it's neater like this. Now let's think about what this really means. If we had some parabola y equals x squared, but we actually wanted to graph this, then what we'd be graphing is the values of y that are sitting underneath the parabola. Now ours is a little like that, except it's minus x squared, which means it's upside down. And if we rearranged it a little bit, then it's minus g over 2v squared x squared. So this is just going to be a dilation factor, making our upside down parabola a little stretched somehow. And then we've got this plus v squared over 2g. So it's an upside down parabola that's stretched out a little bit, that's been lifted up a certain amount. So if we were to graph this, it's actually going to be something like, oops, it's going to, terrible graph, let me start again. If we were to graph this, it's been lifted up, but not necessarily across. It's got a dilation in x, but that's just stretching it. And so then when x equals 0, y is going to equal v squared over 2g. And we could find this point out here by letting y equal 0. And that's going to happen when we can solve all of that. But basically, what does this mean geometrically about this point? Well, what it means is that our point must actually lie underneath this parabola. So basically, to answer the question, x, y must lie under the parabola with this formula. Okay, now we've just found this point here, v squared 2g. Can we find this point out here? Because we know that we're only going to be looking at positive values of x. So since it's shooting the thing from the origin, half of the parabola makes no sense. And we want positive values of y. So this part of the parabola also makes no sense. So we're saying that it's going to be on or under this parabola here, our point xy. So finding this point seems important. Now on the parabola, if we let this be equal to, and say let's let y equal 0, then we would have v squared over 2g is equal to g x squared over 2v squared. So that means that 2v to the power of 4 is equal to 2g squared x squared. We can cancel both of the 2's out. So that means that x squared is equal to v to the power of 4 over g squared. So x is going to be the square root of that, which is v squared over g. So we've found this point out here, v squared over g, and now we've found some parameters for where the point xy must sit relative to this parabola. So quite a tricky little question. Some of these will be easier than that, others will be tricky like this. The key is to read the question really carefully and keep coming back to it if you're stuck, and look for things that are familiar. Here we just needed to look for the fact that this was an upside down parabola and then think about what we could find out about it to solve our problem.